So there will be a bunch of tests that we're going to consider when we're trying to analyze infinite series for convergence. And the first, most basic one that you really need to check first, because if it fails this, then it has no shot of converging, is the nth term test. So what that says is that if your infinite series converges, it must be the case that the limit of a sub n equals 0. In other words, the limit of the sequence of numbers that's determining the terms, that has to be going to 0. As stated, this isn't very useful, but if you take the contrapositive would mean to negate the conclusion. So if the limit of a sub n as n goes to infinity does not equal 0, that's logically equivalent to, the statement I'm about to write is logically equivalent to the original if we negate the premise. So the infinite series diverges. Does not converge, which means to diverge. So that gives us a quick test. All we need to do, or I shouldn't say all we need to do, the first thing we need to do is just make sure that our terms are going to 0, because if they're not, we can immediately state that it diverges. So this first example here, we've got the infinite series of 1 plus 1 over n to the n. But if you look closely, we know that from a previous unit that the limit of this is not 0, it's e. And what that basically means is in the long run, the terms are approaching e, so it's as though you're adding e, or a number close to e, to itself over and over and over again, which clearly is going to go to infinity. So this implies, so that's not 0, which means that this must diverge. Now you got to be careful when you apply this test. It can never be used to prove convergence. If you read very carefully, it doesn't tell us when something converges. It just says what has to be, if something converges, we know for sure what the sequence is doing. So, for instance, let's look at this example here. 1 over n, also known as the harmonic series. If we take the limit as n goes to infinity, this is 0, right? However, that doesn't mean it converges. We're going to see that there are terms that there are series whose sequences go to 0, but they diverge. So I'm not going to answer this question now. I'm just going to write may converge, but it may not. More analysis needed. Just for now. And we'll revisit this later to see what actually happens. So as we've seen, a geometric series is one in which we know pretty much everything about. If we recognize a series has this structure, we can figure out if it converges or diverges based on the r value. And if the r value has absolute value less than 1, then we know that its sum is this. So not only do we know what test to apply to see if it converges or diverges, we also know what the sum is if it converges. So in this example here, it looks like we've got a first term of a 2, and it looks like if I can find my common ratio, I can apply the test above. So to get the common ratio, you can always just take a term and divide by the one before it. So if you do negative 8/3 divided by 2, that is negative 8 over 6, which is negative 4/3. So that's my common ratio. And the absolute value of negative 4/3 is, so again that's my r value, but the absolute value of negative 4/3 is bigger than 1. So this must diverge. If you look at the second example, this looks a little crazy. I put this here to give you a property that's useful, and that is you can separate this into two, view it as two different series added together. And so the reason I'm saying that is because now, if either one of these diverges, the whole thing diverges. However, if they both converge, then we just add the sums of what they each converge to. So this first expression, you might want to think of it as 1/3 all to the n. And you might want to think of the one on the right as -1/2 raised to the n. And so that's useful because now what I can do is view this as a geometric series in which my first term is 1/3, and my r value is also a third, which is less than 1. I should say its absolute value is less than 1. And so therefore its sum is first term divided by 1 minus a third, which is a third divided by 2/3, which is a third times 3/2. So that's a half. And the second series here has a value equal to -1/2, and the absolute value of the r value is the absolute value of -1/2. That's also less than 1, so it converges as well. So that must mean its sum is equal to the first term over 1 minus the r value, which is -1/2 divided by 1 plus a half, which is 3/2, which is -1/2 times 2/3, which is -a third. And that means that this series here is equal to the value of the first series, which is a half, minus a third, which is 3/6 minus 2/6, which is 1/6. All right, so again, the point of that was just you've got a series that can be broken up and separated into two geometric series, which can be analyzed separately. Here we're going to look at another type of series called the telescoping series, and we can actually find the sum of these as well if we use partial fractions to rewrite the terms. So the first thing I usually do is I'm going to rewrite this as a finite series. So just going to replace the infinity with a k. And then what we'll do is we'll see if we can get an expression for this. And then just take the limit as k goes to infinity to actually see what it sums to. So, over here on the side, note that I can use partial fraction decomposition to write this as a over n plus b over n plus 1. And I know that to get the common denominator, I need to multiply the top and the bottom of the left term by n plus 1, and the right term by n, which means that I can equate the numerators. And so when n equals -1, that means that b times -1 is equal to 1, so b equals -1. And on the other hand, if n equals 0, we see that a is clearly equal to 1. So that tells me I can rewrite, I'm just going to use this, I'm just going to isolate the finite series there. So that can be written as a over n, but a is a 1 over n, plus b over n, which is negative 1, so negative 1 over n plus 1. And now watch what happens when we write out the terms. This is equal to, when you plug in a 1, you get 1 minus 1 half, plus, and then when you plug in 2, you get a half minus a third, I'm not happy with how I wrote that. Sorry. 1 minus a half plus a half minus a third. Alright, plus, then when you plug in the third term, you get a third minus a fourth. Etc. until the kth term, when you plug that in, you get 1 over k minus 1 over k plus 1. Now what you can see what's going to happen, since this is a finite series, we can use the associative property, and those will go away when added together. Those will go away. All the inner terms will go away. The only thing we're left with is 1, the first term, or that first value there, and then a minus k plus 1 over k plus 1. So that's the sum of the finite series. So remember, we're going to take the limit as k goes to infinity of 1 over 1 minus, or 1 minus 1 over k plus 1, and that equals 1. So that's the value of this. That's the value of this series. I'll get this one here started for you, and then I'll let you try it on your own, and I'll just tell you what it equals. It should equal a half if you do your analysis right. But the first thing to do would be just to get you started, would be to factor this into 1 over n plus 1 times n plus 2, and then use the technique above to see if you can show that it goes to 1/2.